Welcome to Module 11, Linear Optimization Models. This is the final part of our data modeling section, and also the second module in prescriptive analytics. So far, we've learned how to describe what has happened through descriptive models and how to predict what might happen through predictive models. And now, in this final stage, we move from understanding the data to making decisions with data. So in this module, we will explore how optimization models help decision makers find the best possible solution under given constraints, whether it's the maximizing profit, minimizing cost, or efficiently allocating resources. An optimization problem is all about finding the best possible solutions from all feasible options. Best can mean maximizing something we want, like profit or efficiency, or minimizing something we don't want, like cost or time. Optimization is used everywhere, in business, engineering, and data analysis, whenever we need to make the most efficient use of limited resources. For example, a manufacturer wants to meet demand while minimizing cost. A financial analyst wants to maximize investment returns. A marketing manager wants to get the best result from a fixed advertising budget, and a logistic planner wants to minimize transportation costs between warehouses and customers. So linear programming is a specific optimization problem with linear objective functions and constraints. In other words, all relationships among the variables can be expressed using linear equations or inequalities. This approach is commonly applied in areas such as resources allocation, production planning, and rescheduling, where the goal is to make the most efficient use of limited resources. Every linear optimization problem, or all optimization problem, has three key components. Objective function, which is what we want to maximize or minimize. Constraints, which are the limits or requirements, like budget or capacities. And then decision variables, which are the controllable inputs we adjust to find the best outcome. So linear programming is widely used for resources allocation, product planning, and scheduling. Basically, anytime we want the best result under limited resources. And there are four characteristics. Linearity, which is all relationships between variables are linear. Objective functions and constraints that are similar to the key component. And the last one is non-negativity, which is variables that usually cannot be negative. For example, you cannot make a negative number of product. So do you remember what we have done in section 2 using the Power Inc. as the example? What we were talking about in the section 2 is how we start with understanding the business context, knowing the objectives, and then identifying all the constraints that shape the decision. And we've talked about the 6 steps of how we can formulate a problem to a mathematical statement. And the first 2 steps are understanding the problem thoroughly and clearly define the business objective. And then we identify the constraints, which are the rules or the limits that must be respected. This might come from the budget, resources, regulation, or operational boundaries. Like the cost has to be less than the budget, or the quantity has to be more than 0. And then we also talk about you have to make sure you have to define the decision variable, which is the thing we control. So in marketing, that could be the budget for each advertisement channel. In inventory, it could be the reorder quantity. So these are the variables turn business levels into math terms, making them analyzable. And then that has to be the variables we can control, and it can affect the final result, which is our objective. So once the variables are set, we can write objective functions, and we can write the objective functions using the decision variables as well as the constraints in the decision variables. So we use this example, which is the Par Inc., and we know that the company plans to produce the two modules of the golf bags, the medium and high priced, a standard one and a deluxe one. And then each module requires time in 4 departments: cutting and dyeing, sewing, finishing, inspection, and the packaging. And the constraints very clearly that the Par has limited labor hours available across departments over the next 3 months. They only have 630 hours for cutting and dyeing, 600 hours for sewing, 708 hours for finishing, and 135 hours for inspection and packaging. And then they defined the profit, which is the $10 for standard bags and $9 for deluxe bags. So these are the parameters and constraints we already understand. So what they want how many of each type they should produce to maximize profit without existing time limit. And so in this case, if you go through the 6 steps we're talking about, so the first step, understand the problem, so that we have to design how many standard bags and deluxe bags to produce. That's the number, which is the problem. And then the objective is to maximize the profit. So how many products, that's the number, and to maximize the total profit, that's the objective. And then we talk about the constraints, which are the time limits for each department, and as well as the non-negativity constraints and integral constraint. So non-negativity means we cannot create bags that is less than 0, so they have to be positive. And also the integral constraint means the number of the bags must be an integer. We cannot produce the 1.5 bags or 2.3 bags. So it has to be a 1 or 2. So they both has to be, the number has to be the integer. So these two are, we call it limited constraints. Sometimes we don't talk about it during the business discussion, but they have to be there. Alright, so after that, we define the decision variables. And since the numbers are the problem, so we define the decision variable based on our problem. So we defined number of deluxe bags and number of standard bags and number of deluxe bags as our decision variable, and we use S and D to represent it. So S equals the number of standard bags and D equals to the number of deluxe bags. So they are referred to decision variables. And then after we have the decision variables, we can use decision variables to represent the objective. Since the profit of standard bags is $10 and the profit for deluxe bags is $9. So we know that the total profit should be 10 multiplied by S, which is standard bags number, plus 9 multiplied by D, which is amount of the deluxe bags. And since our objective is to maximize this profit value, so the objective in a mathematical version should be maximize of 10S plus 9D. And the last step is we can generate the mathematical equations for constraints. And so we know that the constraints in the parts production is a limited number of hours available in each department. So, for example, for the cutting and dyeing, each standard bags requires 7 tenth hours, and each deluxe bags requires 1 hour. So the total production time is actually 7/10 multiplied by S, which is the amount of the standard bags, and 1 multiplied by D, which is the number of deluxe bags. And in this case, since the constraint of the cutting and dyeing is 630 hours, so we can write this constraint as 7/10 S plus 1D less than or equals to 630. So this is how we transfer the constraints to a mathematical equation or inequality using the decision variables S and D. So use the same way, we can finish inequalities of all the constraints by using the same method. At the end of the 6th step, don't forget about additional constraint, which is the S and D has to be more than 0, and S and D, they has to be the integers only. So by completing these 6 steps, we've built clear optimization models for Par Inc. That the balanced limited labor resources again is profit contributions from two production type. And this model allows decision makers to calculate the production mix to maximize the profit. And this is a perfect example of how the prescriptive analytics turn business strategy into actionable decision. And now let's see how exactly we do it. And now let's see how we exactly do this in the Excel. All right, before that, let me explain why we call this problem is a linear programming model or linear program. Because both of the objective function and all the constraints are linear functions of decision variables. A linear function means that each variable appears by itself, raised only to the first power, no squares, roots, or production of variables. This assures that the relationships between variables are proportional and consistent across the model. So let's look at the one of the constraints, which is for cutting and dyeing. So we know that the constraint for cutting and dyeing is 7/10 S plus 1D less than 630. We can actually write this as the D equals to minus 10/7 S plus 630. And then if we think S as X and D as Y, and we can get a straight line equation, which is Y equals to negative 0.7X plus 630. So this is actually a linear relationship between X and Y. And we can check about the graph about this equation. This is a straight line. And that's why we call this linear programming. And because all of the constraints and objective functions follow this same linear pattern, so the entire model is recognized as the linear program. So similarly, the functions on the left-hand side of all the constraint inequalities are linear functions, right? So the mathematical formula of this problem is referred to as the linear program. Since we've already know that the power problem is a linear program, so let's discuss how we might find the optimal solution. The optimal solution must be a feasible solution. A feasible solution is a setting of decision variables that satisfy all of the constraints of the problem. So to solve a linear program, then, we must search over the feasible region, which is the set of all feasible solutions, and find the solutions that gives the best objective functions value. So what exactly is feasible region? When a model has two decision variables, we can visualize it as the two-dimensional space. For example, the x-axis represents the standard product, and then the y-axis represents the deluxe products. And each linear constraint forms a straight line that divided the plane into two parts. The line and one side of it represented all combinations that satisfy the constraints, and that is called a half space, or is also called feasible region for this specific inequalities. And then the feasible region is formed by the intersection of all of this half space. It shows every point that meets all constraints at the same time. So for example, the constraint less than or equals to negative 7/10 S plus 630 includes all points below and on the line D equals to negative 0.7 S plus 630. So this area, we called it the feasible region. Non-negativity constraints further restricted this area to be above the x-axis and to the right of the y-axis. Multiple constraints, which means we have multiple lines, the feasible region is formed by the intersection of all of this half space. So thus, the non-negativity constraints define the feasible region as in the area bounded by the horizontal and the vertical axis, and each of the four constraints is graphed as equality. The line and the areas shows the direction of the half space that satisfy the inequality constraints. And then the intersection of the half space, which is the shaded region, is the feasible region for the power problem. and any points in this shaded region satisfy all four constraints and non-negativity. So to solve the part problem, we must find the point in the feasible region that will result in the highest possible objective function value. So let's see the example. We can now define an objective function which is 10s plus 9d conquered to be a set of the points that yields the fixed value of the object function. So let's see this point. So this is the points of negative 7/10s plus 630 equals to negative 2/5s plus 540. So at this point, the s equals to 300 and d equals to 420. So when the s equals to 300 and d equals to 420, 10s plus 9d is 6,780. So this is the profit when we have 300 standard bags and 420 deluxe bags. So what we will do is we will try to find the s and d at those points that can maximize the profit. So as we move away from the origin, we see the higher values of the objective function. Then we can find point 1, 2, 3, 4, 5. Those are the extreme points of the feasible region. And we can obtain the s and d by solving similarity as equities, and so the pair of the constraints that forms the given points. And as a result, based on this table, we can see that the highest concord is 10s plus 9d equals to 7,668. And when the s equals to 540 and d equals to 252. So at this moment, we can see that the highest profit is achieved at point 3, and the obtained plan is to produce 540 standard bags and 252 deluxe bags with the highest profit, which is 7,668. And now let's see how to solve linear program within the Excel. So at first of all, we have to construct a relevant what-if model. So a what-if model allows the user to experiment with different values for the decision variables and observe whether each trial solution is feasible, as well as determine the corresponding values of the objective functions. So, first of all, in this spreadsheet model, we have to use a trial solution of 1 standard bag and 1 deluxe bag. So we have to set up the parameters that define the problem. So here, let we put the names of the par income, and then we have parameters. And the parameters including the production time of each operation, as well as the available time. And under the production time, we should have standard and deluxe bags because they have different production time. So we have these operations. And then we're going to start by the model. So the row 14 holds the decision variable cells, where B14 and C14 specify the quantity of standard bags and deluxe bags that to be produced. So these are the decision variables, and we can change these numbers. So we can change these numbers to what? To calculate the profit, right? So in this case, in row 16, we're going to calculate the objective function value. Okay, and then after that, we will have the constraints from start by the row 18. And then we also have the times for standard, deluxe, as well as the time availables. At the end, we also have parameters which are the profit per bag. So we have $10 for standard bags and $9 for deluxe bags. We're gonna calculate the objective function value by using the sum product function. So the sum product function is to multiply the related sales from the different cross tabulation. So for example here, when we're using the sub product function on B9C9 to B14C14, that actually means use B9 multiplied by B14 plus C9 multiplied by C14, which is so far $10 multiplied by 1 of standard bags and $9 multiplied by 1 deluxe bags. That is 19. So far the total profit for 1 standard bags and 1 deluxe bags is 19. So we can use the similar way with the sum product function on different operatings to calculate the hours used. For example, in B19, we have the sum product B5C5 and B14C14. So that actually means we were using B5 multiplied by B14. That is the hours used for standard bags. That is hours of cutting and dyeing used for standard bags. And plus the C5 multiplied by C14. That is hours of cutting and dyeing used on deluxe bags. And so this is the hour used for cutting and dyeing. And so that's why so far it is 1.7 hours. And then on the column C, we would have the hours available. So the hours available for the cutting and dyeing is equals to D5 that we have in parameters, which is 630 hours. So by doing this, we have the current trial solutions that are feasible because the hours used do not exist as available hours in any apartment. But that's because we only have 1 standard bags and 1 deluxe bags. So the next step we're going to do is we were using the Excel solver, which is a powerful add-in for Microsoft Excel that allows us to perform what-if analysis and optimization. Specifically, it helps us to find optimal solutions to complex problems by adjusting decision variables within given constraints. So to use the Excel solver, we have to click the Data tab in the ribbon, click Solver in the Analyze group. If you don't have the solver, here is the Mac. So in the add-in availables, you can click the solver's add-in and click OK, then you'll have the solver. If you're in the Windows, you have to follow these steps. So actually you have to go to the File, go to the Options, and then find the add-ins, and then click Add, and then choose the solver and click OK. So that's how you have the solver in the Windows. Click Solver in the Analyze group. And when the Solver Parameters dialog box appears, we have to enter B16 in the Set Objective box because B16 is the total profit, and that is our objective. And then we select the max for the 2 option. It's because what we want to do is we're trying to maximize the profit within those constraints. And if the goal were to minimize the cost, then the min option would be selected. And if the objective were to reach a specific target value, then we can set that in the value of option. So it is purely based on what is the objective you want. You want to maximize, you want to min it, or you want to set it as a specific value. Then in the by changing variable sales box, we enter B14 and C14. That is because B14 and C14 are quantity of standard bags and deluxe bags, and they are the decision variables corresponding to the quantities of the 2 products. That's because it is the decision variables that we want to change that can impact the total profit. And then we're going to click Add to define the constraints. In the Add Constraints dialog box, we have to enter B19 to B22 in the cell reference field to specify the cells representing the resource usage that must remain within the limit. So B19 to B22 are hours used for the 4 different operationals. And then we have to select less than or equal to condition because we have to make sure that our hours is less than the hours available. The next one, we enter C19 and C22 in the constraint field so that we have to make sure that the numbers of B19 to B22, which is the hours used of each operation, has to be less than or equals to the numbers in C19 and C22, which are the hours available. So this is how we set up the constraint to make sure that those numbers should be less than the constraint. And those hours are calculated by the decision variable, which is the quantity of standard bags and deluxe bags. So when the standard bags and deluxe bags quantity changed, the hours used also changed. And no matter how they change, we have to ask Excel to make sure that the hours will be less than the hours available. And in that case, once the hours used is more than the hours available, the standard bags quantity and the deluxe bags quantity should stop increase. So this is the logic of the solver. And then don't forget to ensure the checkbox for make unconstrained variable non-negative, because we have to make sure that our numbers are all more than 0. And at last, from the select the solving method menu, we choose simple linear programming, which is appropriate for the linear programming problems. And then finally, click solve to run the optimization. When the solver result dialog box appears, we select the keep solver solution to retain the optimized values. And then to generate the summary of the result, select the answer report option under reports and then click OK. So now we have the report that provides detailed information on the optimal solution, the status of each constraint, and then the final value of the object functions. So then we can check about this final answer. So we can see that we have the objective cell, which indicates that optimal value of the final of the total profit is 7,668. That is exactly the value we have before using the concord of the feasible region. And then we have variable cells that indicates the optimal values of the decision cells and whether or not the variables are required to be the integer. So here we have the product of the standard bags is 540 and the product of the deluxe bags is 252. So that exactly the same as what we have before. And then at the bottom we can see that there are constraints, which gives the left-hand side value for each constraint and the formula showing on the constraint relationship and the status and then the select value. So under the status we can see that there are binding constraints or not binding. So the binding constraint means actually that the constraints hold us an equity at the optimal solution. So which means we've used all of the hours that's available. For example, for the cutting and dyeing hour used, the result value is 630 and that is also the available hours. So which means we use all of the available hours on cutting and dyeing. But for the not binding status, for example, for the sewing hours used, we can see that we only used 480 hours. But since the available hours is 600, so which means there are 120 hours stack. That indicates the difference between the real hour used and the available hours. So which means we still have 120 hours to be used. And that can also means maybe we underestimated the hours that are used on sewing hours. So in the future, what decision can make is we can lower the available hours for sewing by exchanging or by transfer the laborers works on sewing to the other options, maybe for cutting and dyeing or maybe for finishing, so that we can have more available hours on cutting and dyeing or finishing, and maybe we can have more products on the standard bags and deluxe bags with more profit.
but overall the final decision for them is they should produce 540 standard bags and 252 deluxe bags to come up with the 7,668 profit, which is the maximized profit they can do in the coming 3 months. All right, so this is the example of the maximize problem. We can also have the example of minimization problem. So let's using another company called M&D Chemicals, which produced the 2 products that are sold as the raw material to companies manufacturing both soaps and laundry detergents. So based on an analysis of the current inventory levels and the potential demand for the coming months, MD's management specified that the combined production for product A and B must total at least 350 gallons. Separately, a major customer's order for 125 gallons for product A must be satisfied. So that actually means the quantity of the product A has to be more than 125 gallons. And then we have other parameters, including the product A requires 2 hours of processing time per gallon, and product B requires 1 hour of processing time per gallon. So for the coming month, totally 600 hours of processing time are available. And the MD's objective is to satisfy these requirements at a minimum total production cost. And at the last, they provided us the information related to the cost, which are $2 per gallon for product A and $3 per gallon for product B. So to determine the minimum cost production schedule, the MD Chemicals problem can be formulated as a linear programming model. So following a similar approach to PAR. Example, the first step is to define decision variables and establish the objective function. So we're going to have A represent the numbers of product A to be produced and B represent the number of the gallons of product B to be produced. And given that production cost is $2 for A and $3 for B, the objective is to minimize the total product cost. As a result, the cost is $2 multiplied by A, which is the quantity of product A, and plus $3 multiplied by B, which is the quantity of the B. So the objective function would be minimize the 2A plus 3B. And next we consider constraints. So based on the description of the background, we know that first of all, they have to meet customers' demand for 125 gallons of product A. So that means A has to be more than 125. And then for the combined production of both products, which must total at least 350 gallons. So we have to write that A plus B has to more and equals to 350. In addition, there's a processing time limitations of 600 hours. And things the processing time for A is 2 hours and the processing time for B is 1 hour. So that means the 2A plus 1B has to be less than or equals to 600. And finally, don't forget about non-negativity constraints as well as the integral constraints. So after we have all of these constraints and the parameters, we can put the parameters and constraints as well as decision variables into the Excel worksheet. So for the parameter sections, we have to put the production time for each product, production cost, and then total available processing time. And then we also have the minimum total production and production A minimum. Those are the parameters. And then we have decision variables in C14 to D14 represent the cells that solver will determine. So they are the number of the gallons for product A and B. And then we will have the objective function cell in C16, represent the total cost that we want to minimize. And then the formula is B5 plus B14 plus C5 multiplied by C14. And we can also use the sum product function on B5C5 and B14C14. So that is actually the cost of the product A plus the total cost of product B. And then we will have the constraints. So in the constraints, we have the product A provided product of product A, it has to be more than required one, which is 125. And total production has to be more than 350. And we also have processing time. And so the hour used of all processing time has to be less than hours available, which is 600 hours. And so then we go to the solver. So similar with the par, we have B16 that represents the minimum total cost. That is the objective function. And then in this case, we will select the minimize total cost. And because the objective is to minimize that cost. And so then in the by changing value cost, similarity than the par example, we have B14 and C14, which are the products, the quality of the product A and product B. And then here we have the constraints set up. So here we see that there are two different kinds of the constraints. One is more, one is less. Because the product A has to be more than a specific value, and then the total quantity has to be more than another specific value. So we put B19 and B20 together. So there has to be more than the C19 and C20. We also have available total hours, operational hours. So we have B23, that is the calculated hour used, and it has to be less than or equals to the available hours. So in this case, we will choose less than and equals to. So make sure that you have the correct operators for all of the constraints. And then at last, don't forget to check about make unconstrained variable non-negativity. And then we're going to select the simple linear programming. And we will click the solve buttons to show the solver result. So as shown right here, the optimal solution is to produce 25 gallons of product A and 100 gallons of product B, resulting in a total cost of 800. So both the total production constraint and the processing time constraint are binding in this case, so meaning that they directly determine the values of decision variables. In contrast, the requirement to produce at least 125 gallons of product A is not binding because the optimal solution exists this minimum. So for contrast, constraints expressed as greater than or equals to inequalities, we introduce a non-activity variable known as the surplus variable. The surplus variable mirrors how much the left-hand sides on the constraint exceed the right-hand sides at the given solution. So right here, the surplus variable is the product A provided, which is 125. And this means there remains unused capacity of flexibility within the condition. So in this case, the stakeholders can think about, we can maybe produce more product A, or maybe we can remove the available hours for product A, which means we can decrease the labors of the product A and put them more to product B so that we can have the more total product. So this is how stakeholder can think about after they see this result. So in addition to the normal cases of the linear programming outcomes, we also have the two special situations that can arise when we attempt to solve linear programming problem. And the first one is called alternative optimal solution. So for example, in a par, we have the optimal solution, which is when S equals to 530 and D equals to 152, right? But however, this is the only one optimal solution. In the real business, resources such as the materials, labor, and production capacity may fluctuate. So when the solution is unique, there is little room for adjustment without reducing profitability. As a result, the production process must adhere strictly to that plan. And if unexpected external factors such as the supply chain disruptions or capacity changes, when this kind of situation occurs, the company has no alternative production combination that can maintain the same level of profit. So to address these kind of limitations, decision makers sometimes accept a slightly lower profit in exchange for greater flexibility and a wider range of the feasible production options. For example, in steel the par company, instead of having 10s as the standard bag's profit, we can decrease this to $6.30. In that case, the objective function becomes 6.3s plus 9d. The reason we do this is we can see from this graph that the revised model shows a key change in the solution landscape. So when the objective function is modified in this way, multiple optimal solutions may emerge. And this happens because the new ISO profit line becomes parallel to one of the constraint line. And this causes a portion of that constraint line to overlap with the boundary of the feasible region. And as a result, the maximum value of the objective function can be achieved at several points along with the line segment instead of at a single point. So in other words, the different combination of S and D yields the same optimal profit. So for example, we can have the S equals to 540 and D equals to 252, which is the profit of $5,670. And then we can also have when S equals to 300 and D equals to 420. That also give us the profit as $5,670. So it doesn't mean like the losing the profit is a problem. So in this case, when something happens, as we described it before, either the supply chain disruptions or capacity changes, we can have different combinations of S and D to come up with the same profit. So this is why a linear programming problem that produces multiple optimal solutions is generally beneficial for the managers and decision makers. It provides flexibility, allowing them to select among several equally profitable production combinations while considering other optional factors such as the resource availability, scheduling, or strategic priorities. And the other special case is called infeasibility, which means that no solutions to the linear programming program satisfy all the constraints, including the non-negativity conditions. So let's see this graphic. We can see that infeasibility means that a feasible region does not exist. That is, no point satisfy all the constraints and non-negativity conditions simultaneously. So to illustrate this situation, we can look again at a problem faced by PAR. And we suppose that a manager specified that we need to have at least 500 of standard bags and at least 630 lecture bags. So that's also a constraint, right? So which means the S should be more than 500 and D has to be more than 630. However, we can see that the shaded area in the lower left-hand portions depict those points satisfying the departmental constraints on the availability of time. The shaded area in the lower left-hand portions represented the points that satisfy the departmental constraints on the availability of time. And then the shaded area in the upper right-hand represented those points satisfying the minimum production requirements of 500 standard bags and 360 lecture bags, but no point satisfying both sets of the constraints. So, thus, we see that if management imposes those minimum production requirements, no feasible region exists for the problem. So how should we interpret the infeasibility in terms of those current problems? First, we should tell the management that given resources availability, it is not possible to make 500 standard bags and 360 lecture bags. Moreover, we can tell management exactly how much of each resource must be expended to make it possible to manufacturing those numbers of the bags. So this is how we can use the solver in Excel to figuring out the linear optimization models for prescriptive analytics in a business.